Hi everyone, today we will proceed with the chapter Limits and Continuity, and this class onwards we will talk about the more advanced portion of this topic, which is like one-sided limits and also the commonly occurring limits, the more advanced technique to evaluate limits, and trigonometric limits, your transcendental functions, and also the epsilon delta definition of limits. Yeah, I reserved that for the last part for this topic because it is like the nightmare for all the Cat 1 students, right? So if you remember from our SDPM past year question discussion, we actually do we actually did the epsilon delta definition proof for one-sided limits, right? And actually from I think very earlier discussion, we also talk about how we evaluate one-sided limits analytically, which is you plug in the value of 1.99999 or 0. Or 2.000001, right? So today we will look at how we evaluate them algebraically. Okay, so I will mainly discuss the exercises from this worksheet 2.4. Okay, so let's start with a starter question. Okay, so we have three limits here. They're actually the same function, just that one is from both sides, one is from the right, one is from the left. Are they different? Okay, so let's ignore the from the right and from the left first. How would you evaluate the first one? Okay, so if you look at it, if you plug in the value of x, you plug in 1 for x, you'll not get anything crazy, isn't it? You will just get a square root of 1 minus 1 is 0, 1 plus 2 is 3, so the answer is 0. They will tell me this is the answer. But is that correct? Think about it, and if you can't see it, let me show you the graph of this function. Yeah. Okay, so yeah, I hope you can see this. This is how the graph of the function look like. And you say that, oh, the limits from the right is actually 0, isn't it? But what about from the left? We have nothing. And remember from our previous discussion and our previous definition for limits, the limits from both sides must be the same. Must be the same unique limits. Then we can say that the limit exists. But in this case, how come after you substitute in, you have a value? This is because if you can substitute in, it doesn't mean that your limit exists. Okay, so let me show you. When we are talking about limits and continuity, we actually care about 4 things, right? If you have a limit when x approach c equals to something, okay, then you have to find f of c, right? You plug in the value of c, see whether it exists or not. Then the second one is x approach c from the right. Then limits when x approach c from the left. Last but not least, the limit when x approach c from both sides. Okay, then we go and compare this value to conclude that whether the limits exist or whether the function is continuous at that particular point. So in this case, if you can sub in the value and you get a defined answer, it only means that your f of c exists. Your f of c is defined. Okay, so this is a little bit different from what we got from our previous discussion, because in previous discussion we always get that, oh, your limit exists. Okay, like for example, a very typical example is like this. You have a hole somewhere in the middle. Yeah, the limit exists because the limit from the left and from the right are the same. But f of c is undefined. And now it is the opposite, which is f of c exists, but the limit does not exist. Okay, so this is the importance why we need one-sided limits. Okay, so let's look at this question here. Okay, but before we start, let me show you something else, which is when we are dealing with limits from one side, okay, so I hope I have enough space here, and in this case it is from approach to 1. If it is approaching from the right, like the second limits here, by the way, this should be wrong, this should be does not exist, okay? Okay, so for the second one, if we are approaching from the right, means your x should be somewhere here, right? And you know that this from your 1 to your x should be a very small number. And I don't want to use epsilon or delta here because I don't mean to write the epsilon delta proof. I will just write a h. Okay, but your h is definitely a very, very small number. So how would you express x in terms of h? It should be a, what's that? 1 plus h, isn't it? So if we are talking about one-sided limits, and we know that we can't just put in 1 into the function, what we can do is, instead of taking x approach something, we take h approach something. And you know that because you want h to be a very, very small number, then we take the limit when h approach 0. Then how do we write the function now? Everything must be in terms of h. Okay, so this is why just now I asked you, how would you express x in terms of h? So obviously, you'll just replace your h with 1 plus h. Your x with 1 plus h. Okay, then minus 1. Then 1 plus h plus 2. And now, what you got? Okay, maybe one more step. H approach 0 of h over 3 plus h. Am I right? And now can you plug in the value for h? Yes, you can. And you will get actually a 0, which is what we saw from the graph just now, right? The limits from the right is 0. No problem. Then what about from the left? If you approach h from the left, you approach c from the left, means your x is somewhere here this time. Okay, x is here. And again, this is your h. Your h is now here. And this times your h should be 1 minus h. Okay? Then you do the exact same thing. Limit h approach 0, of, this time it is 1 minus h. Okay? Then minus 1 minus h, then plus 2. Then what will you get? You have a limit when h approaches 0 of negative h over 3 minus h. Now, my question is, can you say that this is equals to 0 when you plug in the value of h? You may say that, oh, we can, because negative 0 means 0. Then the square root of 0 is still 0. But when we are talking about limits, it doesn't mean that the point is exactly at that point. Okay, we are talking about approaching. So the h here is actually not 0. It is 0.00001 or negative 0.00001, which means it is actually a negative number. And you know that if your anything below underneath a square root is negative number, in the real world it is undefined, right? Undefined or does not exist. Hence, the limit from the left is not the same as the limit from the right. Therefore, the limit does not exist. Clear? So actually, one-sided limits is very simple, just that you have to understand the concept from the left, from the right, and how come we have a h there. And the rest of them, because we are taking h approach 0, every time it must be h approach 0. So Actually, it's very easy. It's usually very easy to evaluate the limits using what the limits evaluating technique that we learned from earlier. Okay, so let's do the exercises. Okay, evaluating one-sided limits algebraically. So before we start, okay, I will just do a very generalization of the idea just now. Okay, so if you see this, the limit when x approach c from the right and the limit when x approach c from the left. So again, your c is here, from the right means your x is here, your h is here. So if you see this, you just go ahead and replace your x with c plus h. Okay, if it is from the left, means your x is here, your h is here, then you replace your x with c minus h. Okay, so these are the two things that you have to remember. The rest are just computing the limits. Okay, let's look at the question. Okay, evaluate one-sided limits algebraically. Look at the question. It is from the right, so we will use the first one. Okay, so limit. Now we are talking about h. Okay, we're talking about h of, remember, c plus h, c plus h, oops, sorry, that's h, then c plus h. Oh, we have a lot of things to do here. Okay, then c plus h. But actually, you know what? You check first. If you plug in the value, or if you plug in h with 0, will you get anything crazy or not? If no, actually you can directly just sub in, So this will just be -2 over, you just take all your h as 0. Okay, your h is all 0. You don't have to care about them. And the bottom, it is just -1. Then for this is actually -4 plus 5, which is a 1. 4 minus 2, so it's a 2. And you have your answer equals to 1. Finish. Okay, so it's actually very simple. Just that the concept is a little bit, maybe you need more time to understand. Okay, so the computing the evaluation part is very simple. Okay, question number 2. So same thing, this time we are approaching from the left. From the left, we use c minus h. So remember, you are now talking about h. Then 1 over c minus h, c minus h, c minus h. Remember the bracket, yeah? C minus h. Okay, be very careful with the bracket. Okay, and you check if you plug in 0, will you get anything crazy or not? Okay, 1 minus 0 plus 1. Okay. So just go ahead and plug in 0. Okay, 0. So you have 1 over 2 times 7 over 1 times 3 minus 1 is 2 over 7. Okay, and this and that cancel, you got a 1. Finish. Very simple, right? Okay, let's look at the next one. Oh, okay, so this one is a little bit more technical because as you can see, we have a absolute value, a modulus. So you have to be very, very careful concerning the positive, negative. Okay, I just gave you a hint. Okay, so step 1, check whether it is from the right or from the left, and this happens to be from the right, so we use c plus h. just go ahead and replace your x with c plus h. Then be careful with the modulus. C plus h. C plus h. Okay, what to do next? Simplify. 1 plus h, absolute value of h over h. What's next? If you directly plug in, what will happen? You have a 0 over 0. Or maybe let me just split it. Anyway, I want to focus on that part. Limit when h approach 0 of absolute value of h over h. Okay. So, you know that if you have a function of f of x maybe, okay, okay, equals to the absolute value of x over x. How does the function look like? It is actually 1, isn't it? It is 1 when your x greater than 0. It is negative 1 when your x is smaller than 0. When your x is equals to 0, it is actually undefined because it is 0 over 0 and it is indeterminate. Okay, so the graph is actually something like this. 1, negative 1, then a hole, something like this. And now you ask yourself, is your h from the right or from the left? And this time you have to consider whether it's from the right or from the left. So you have to come back to the question. You are approaching negative 2 from the right. If you are approaching negative 2 from the right, let's take something from the right which is negative 1. Okay, something on the right. Let's take maybe negative 1. Then if your x is negative 1, what happened to you? This one. Okay, your x plus 2, negative 1 plus 2 is actually greater than 0. Greater than 0. Okay, which means this x plus 2 over x plus, this absolute value of x plus 2 over x plus 2 will be positive. So you are taking the positive portion of this graph. One more time. Look at the question. It is from the right. At the right side of negative 2, you have negative 1.999999. If you plug in 1.99999 for x plus 2, you will get a positive number. Hence, x plus 2 over absolute value of x plus 2 over x plus 2 will be positive. Hence, you take the positive h. If your h is positive, means this is actually just 1 times 1, then you got a 1. Finish. Okay? And now look at this question 3b. It's exactly the same function, just that this time we are approaching from the left. Then it's actually the same procedure. Just take the limit, h approach 0. If it is from the left, remember it is c minus h. Okay? C minus h, then the absolute value c minus h, c minus h. Okay, then simplify of 1 minus h, limit h approach 0, negative h over h equals to what now? Okay, so now you are actually considering your negative portion of h, isn't it? Okay, and if you want to use the same idea from just now, you are approaching negative 2 from the left, which means it is negative 2.000001. If you plug in negative 2.00001 plus 2, you have a negative answer. Okay? Which means you have to consider this part. So the answer is 1 times -1, which gives you a -1. Finish. Okay, so if you still not convinced, then you can just go ahead and decimal see how the graph will look like. It's actually 1 and the limits are actually different. The limits from both sides are actually different, so the limit actually doesn't exist. Okay, so this is all for one-sided limits. Actually, the computation is very simple. Just that you have to understand this, you have to remember this, c plus h and c minus h. Right, so that's all for one-sided limit. And for the next part, we will talk about trigonometric limits. Okay, using the very famous limit, which is your sine theta over theta. Okay, when your theta approach 0 is equal to 1. Okay, we'll talk about this in the next part.